Hi everyone. You hear me well? Okay. Okay. I want to try just for a moment this. Okay. So hi, I'm Giovanni Zullo from Politecnico di Milano. I'm a nuclear engineer. I have not a background on computational science. But I do a lot of modeling and simulation for our application. And today I want to show you this bunch of Python scripts that I made up in the last couple of years, mainly to help me for some thermomechanical analysis and some related stuff. So I wanted to give you just a quick idea of what I study. Essentially, I mainly study the behavior of nuclear fuel elements. So essentially, nuclear materials, and with usually tough material properties that changes a lot because of the neutron irradiation. To do this particular study and extract figure of merits that are useful from an engineering point of view, people usually use codes that are proprietary and okay from a regulatory point of view. In research, these codes sometimes can be used, but recently there has been a lot of effort towards going to an open source alternative in terms of modeling. I did mostly fission gas behavior, fission product behavior, so transport of something in fuel. I wanted to try to do something also on a more engineering scale. On that side, you can see an example, a schematic of a fuel rod, essentially a tube with some fuel inside that is heated, and that is usually in nuclear reactors. Okay, so what I did essentially was to collect the Python script that I was using, based again, of course, on FEniCSx, in a sort of structured way. I have a couple of scripts that start by reading some input quantities that for me are, but for everyone, I guess, are a geometry, a mesh. And then I started collecting input settings, let's say, to start simulation in YML file, collecting solver settings, boundary conditions, material properties, and so on. Then all these plain text, let's say, file are read from some Python scripts that are somehow ordered. It means that there is a reader, of course, and then a set of physical models that I implemented so far, essentially the thermal model, the mechanical model. I added some damage model, again, physical phenomena that are useful. And then all this physics goes inside a solver. The solver that for now is a staggered solver. So each physics is solved once at a time. And the output is a paraview file, essentially. This is the basic structure of the code. I can go fast on this because essentially what I liked a lot of FEniCS is that we can use automatic differentiation. Essentially is a very nice feature that I liked a lot, but you all know, of course. I would just skip a bit to the solver, saying that essentially, since sometimes the physics solved in time are very stiff, I had to apply some algorithm essentially up to now in the solver strategy there is an adaptive relaxation with the relaxation factor which can be fixed or not in the input file, and sometimes there can be also some adaptive time stepping if needed. Then just a word on multi-material domains, because again I started doing this to study some materials of interest for me. In particular, nuclear fuel elements are essentially a tube of metal with a set of pellets of oxide inside. So two materials, a tubes in another one with a gap. And I could implement some strategy to model the transfer again among two materials. The nice thing, I guess, is that all this multi-material stuff, I automated this a bit in the sense that from the input file, one can define a sequence of materials. If these materials are inside the mesh, and if you give the correct boundary conditions to each material, then all the structure, the solver is somehow automatic, and the solution of the transfer or coupled phenomena between multi-material is somehow automatic from this point of view. Just a quick word on the verification. I mean, we know perfectly that finite element works. The point is that always thinking from a regulatory perspective, when you have a code, and when you say that you have a code that solves some equations, you should say always that you are solving the good equation. So in the repository of the code, I put many cases, analytical cases, in which each case is essentially made of an input file and also some Python regression files, just to check that the output match the analytical solution, so that each physics that is implemented, the thermal, the mechanical, the damage, nonlinear phenomena, are all verified. And this is an important step for us. But as an example of this multiphysics framework, I want to show you this, that I will try to guide you a bit. Essentially, imagine to have a fuel rod, so two cylinders, a cylinder of oxide of uranium dioxide, which is heated, and a cladding outside of metal. And from an engineering point of view, we need to assess the temperature to be sure that the material are not melting and they don't fail. What is nice is that with all these physics implemented, I could check this quantity. The blue curve on that plot is the distance between these two bodies that gradually decreases. Okay, that behavior that decreases immediately at the beginning, then goes up a bit and then goes down again, are a bunch of nonlinear phenomena. We start with thermal expansion, then with some densification phenomena that are physical process that happens in the fuel. But the point is that when, as the gap is closed, the two bodies are in contact, and there is a contact pressure, of course. Which may seem very obvious, but from a point of view of implementing and so on, it's very nice. It's very didactic also, and it gave us the possibility to study nonlinear laws particular, because, for instance, here I implemented nonlinear creep laws very quickly because the environment was set up, so I could see a contact pressure which, against other usual codes that we used, I mean, it's a really quantity of interest. I will skip this is the temperature and the gap conductance effect because I'm a bit late. I want to spend just a few words on a case that this one that essentially connects three physics together: thermal, mechanical, and the damage, phase field formulation for the damage, which tries to represent a physical phenomena that has been recently, is being studied a lot in the nuclear field, which is the fracture of fuel pellets. Essentially, there was this cylinder, very hot, and then cooled down in this region, and I try to reproduce the same behavior, essentially. So to impose a temperature, to have a temperature transient, and then to have this feedback, this coupling between physics, the mechanical and the damage, and the damage propagation here. No? Okay, that kind of follows the crack behavior observed experimentally. So I will stop here at the end. Thanks for listening. If you have questions, of course, I will be happy to answer here and maybe also later in the demonstration. Thanks.
Thanks, Giovanni.
Thanks.
Is there any question from the audience? Yes.
Just out of curiosity,
yeah.
Thanks for the nice talk. Because you say you implemented it in a staggered way, so when the user switches on different kind of physics, how stable is it? Because if you solve every physics one after the other,
yeah.
you often experience.
Yeah. It's one after the other. There is a single sequence of weak formulation, one for the thermal problem, the mechanical, and so on, and they are solved one after the other. And there is a check for instance, for the thermal problem is on the temperature. If the temperature after each staggered iteration stabilizes, I can say, okay, I reached the tolerance that I wanted. And this is done for every quantities of interest: the temperature, the displacement, the damage, this kind of stuff. Okay.
Oh. Yes.
How have you implemented the temperature dependency of material properties?
Yeah. I see that I could do with Python. Essentially, you can declare a Python function, like I don't know if I have something written here, but like a thermal conductivity, K as a function of the temperature. You can define it, and then decode and then FEniCS will see, okay, there is a formula. It can be imported as a Python package or something.
It's not coming from a table or something.
No, it's a formula, and that is very nice because you can express material properties as a function of the temperature or something else, like the burn up, and taking account on these nonlinearities.
Yeah, we had a question there. Yeah.
Thank you for the talk. Do you plan to account for the potential position changes due to like fission products or?
That is very nice because I did my PhD on that, and at Politecnico di Milano we developed SHANTIX, has been developed by my supervisor, which is a C++ code for to study fission gases and their transport. What is nice is that with stuff like Python binding, you can do this. I plan to do this kind of analysis, like having a local concentration of fission gases inside the fuel, inside materials. But I would say yes, but with coupling. With a coupling with other open source tools, if possible, that gives a lot of values in research activities.
We had a question for Jack. You had a question. Oh, yeah.
Okay, thanks. Yeah, you talk at multiscale in the title, but how do
Yeah, I stepped a bit. Yeah, you're right. I was a bit fast on that. In my view, it's like this kind of analysis. I mean, like because we can. I would like to study the engineering scale of the fuel rod, which is an object that is very thin, 1 centimeter and 3 meters long, which is can be studied at a macro scale, but then with either some material properties or with couplings with other code, one can try to inform from a lower scale the whole engineering simulation, the other scale, from the lower to the...
We're actually trying to do the scale transition, but
yeah.
It hasn't been done yet.
I did it just with material properties that depends on something, like on temperature or on burn up, saying that I know that the effect of fission gases is that one and will impact the thermal conductivity in this way. But you're right saying that from a more rigorous point of view, a real multi-scale probably you can do it when you have coupling with codes that operates at different lengths. Yeah. Up to now is made just with some material properties informed, but in another way, like offline coupling, let's say, not really online.
I think for the sake of time, we can go to next speaker. You're exactly on time, so that's
thanks a lot.